The circular slide rule incorporates windows and indices for solving navigation and flight planning problems. When setting a problem on it, it is good advice to line up the 10 and the 10 as shown. The red cursor may be used to assist in lining up various numbers. The first example that we will do is one involving ratios. In the above ratio, if P equals 25, Q equals 8 and B equals 9.5, what is the value of A? Orientate the CRP-5 so that the 8 is positioned under the 25, like in the ratio. If you move the cursor to 9.5 on the inner scale, you can read 29.7 on the outer scale. To be honest, the calculation is best approached using an electronic calculator. Although division can be done in a similar way to ratios using the circular slide rule, 462 divided by 17.9 equals 25.8 is best solved using a calculator. The same is true for multiplication. 0.015 multiplied by 0.26 equals 0.0039. Although we recommend that you remember your basic conversions, there are some very nice reminders on the CRP-5. Do try and remember that there are 3.28 feet in 1 metre. However, if you cannot remember, line up the 10 on the inner scale, also shown by the red arrow, with the 10 on the outer scale, and notice kilometres, metres, litres is written in red above it. With the cursor positioned on feet in red on the outer scale, you can read 3.28 on the inner scale. Now to an example. How many feet are there in 4727 metres? Line up 4727 on the inner scale with the metre datum on the outer scale. Then rotate the cursor to the feet datum on the outer scale and read off 15,500 feet on the inner scale. Of course, this type of question may be done using an electronic calculator if you know that 1 metre is equal to 3.28 feet. 4727 metres when multiplied by 3.28 equaling 15,500 feet. Important distance conversions to learn are: nautical miles multiplied by 1.15 equals statute miles. Statute miles multiplied by 1.6 equals kilometres. And metres multiplied by 3.28 equals feet. This can be shown on a CRP-5 as follows. Position the 10 from the inner scale under the red nautical mile datum on the outer scale. The cursor is lined up on the red statute mile marker on the outer scale. Underneath can be read 1.15 on the inner scale. Without changing anything, underneath the red kilometre datum may be seen 1.852 kilometres. Let's convert 2650 kilometres to nautical miles and to statute miles. Using a calculator, 2650 divided by 1.6 equals 1656 statute miles. 1656 divided by 1.15 equals 1440 nautical miles. 2650 kilometres may be directly and more accurately converted to nautical miles by dividing by 1.852 to give 1431 nautical miles. Let's convert 363 nautical miles per hour to statute miles per hour and kilometres per hour. Using an electronic calculator, 363 knots multiplied by 1.15 equals 418 statute miles per hour. 418 statute miles per hour multiplied by 1.6 equals 669 kilometres per hour. And more directly and accurately, 363 knots multiplied by 1.852 equals 672 kilometres per hour. Important volume conversions to learn are imperial gallons multiplied by 1.205 equals US gallons, and imperial gallons multiplied by 4.54 equals litres. This can also be shown on the CRP-5 by lining up the 10 on the inner scale with the red imperial gallon datum on the outer scale. Underneath the red US gallon datum on the outer scale may be read 1.2 on the inner scale. Without changing anything, underneath the red kilometres metres litres datum may be read 4.54. Let's convert 25,200 litres to imperial gallons and US gallons. Using an electronic calculator, 25,200 divided by 4.54 equals 5551 imperial gallons. 5551 imperial gallons multiplied by 1.205 equals 6689 US gallons. £2.2 equals 1 kilogram. Let's convert 4290 pounds to kilograms. Using an electronic calculator, 4290 pounds divided by 2.2 equals 1950 kilograms. When we convert between volumes and weights, we must consider specific gravity. Water has a specific gravity of 1.0. 1 litre of water weighs 1 kilogram. Aviation fuels are less dense than water and have specific gravities between 0.72 and 0.82. This means that aviation fuels weigh less than water by fractions of between 0.72 and 0.82. On the CRP-5, line up 1 litre represented by 10 on the inner scale with the red kilometres metres litres datum on the outer scale, and position the red cursor on a fuel specific gravity of 0.74. This now corresponds to 0.74 kilograms on the inner scale. 0.74 specific gravity means the fuel is less dense, therefore weighs less. A reminder: imperial gallons multiplied by 1.205 equals USG. Imperial gallons multiplied by 4.54 equals litres. The volume of fuel multiplied by specific gravity equals weight, and kilogram multiplied by 2.2 equals pounds. An example: convert 708 imperial gallons of fuel with specific gravity of 0.74 into USG, litres, kilograms and pounds. 708 imperial gallons multiplied by 1.205 equals 853 USG. 708 imperial gallons multiplied by 4.54 equals 3214 litres. 3214 litres multiplied by a specific gravity of 0.74 equals 2379 kilograms. And 2379 kilograms multiplied by 2.2 equals 5234 pounds. There is a conversion scale at the bottom of the circular slide rule. Just read from one scale to another to convert temperatures from Celsius to Fahrenheit and vice versa. The formula to convert Celsius to Fahrenheit is Celsius multiplied by 9 divided by 5, then add 32. And the formula to convert Fahrenheit to Celsius is Fahrenheit minus 32, then multiply by 5 and divide by 9. For example, what is 37 degrees Celsius in Fahrenheit? Multiply 37 by 9 and then divide by 5 and then add 32, equaling 98.6. Let's try another. What is minus 40 degrees Fahrenheit in Celsius? Subtract 32 from minus 40, then multiply by 5 and divide by 9, equaling minus 40 degrees Celsius. Speed as a distance measured over 60 minutes can be expressed as a ratio. For example, how many minutes will it take an aircraft to fly 124 nautical miles if its ground speed is 178 knots? This is best approached using an electronic calculator. 178 divided by 60 equals 124 divided by time. Solving for time gives 41.8 minutes. To calculate ground speed, the same equation can be used. For example, if an aircraft covers 138 nautical miles over the ground in 68 minutes, what is its ground speed? Speed divided by 60 equals 138 divided by 68. Solving for speed gives 122 knots. To calculate distance, use the same equation. For example, an aircraft has a ground speed of 354 knots. How many nautical miles will it cover in 94 minutes? 354 divided by 60 equals distance divided by 94. Solving for distance gives 554 nautical miles. Problems involving fuel are solved in a similar way to speed, distance and time problems. For fuel problems, the ratio is fuel consumption or flow divided by 60 equaling fuel available or used divided by time. Let's try an example for fuel consumption. If 5450 kilograms of fuel is consumed in 73 minutes, what is the fuel consumption in kilograms per hour? Substituting into the equation, fuel consumption divided by 60 equals 5450 used divided by 73. Solving for fuel consumption gives 4480 kilograms per hour. Another example, this time for fuel. If fuel consumption is 16.9 imperial gallons per hour, how many imperial gallons will be used in 17 minutes? Substituting into the equation, 16.9 divided by 60 equals fuel used divided by 17 minutes. Solving for fuel used gives 4.8 imperial gallons. Another example, time. If fuel consumption is 510 US gallons per hour and total fuel available is 3,260 USG, calculate the endurance of the aircraft in minutes. Substituting into the equation, 510 divided by 60 equals 3,260 divided by time. Solving for time gives 384 minutes. If you line up the 10 with the 10, an ISO atmosphere is created on the CRP-5, and in the airspeed window, a pressure altitude of 0 feet will line up with plus 15 degrees Celsius. It may be seen that rectified airspeed on the inner scale, for example 170 knots, is the same as true airspeed on the outer scale. TAS can also be calculated in the non-ISO atmosphere. For example, pressure altitude is 18,000 feet. Correct outside air temperature is minus 30 degrees Celsius. RAS is 170 knots. What is TAS? Using the airspeed window, line up 18,000 feet against minus 30 degrees Celsius. Rectified airspeed is shown on the inner scale marked in red here, and true airspeed is marked in red on the outer scale here. 170 knots RAS on the inner scale is lined up with 220 knots TAS on the outer scale. Let's look at another example. Pressure altitude is 35,000 feet. Correct outside air temperature is minus 47 degrees Celsius. RAS is 280 knots. What is TAS? Using the airspeed window, line up 35,000 feet against minus 47 degrees Celsius. This time, using the red cursor, 280 knots RAS on the inner scale lines up with 500 knots on the outer scale. This is an uncorrected TAS. Using the compressibility correction window, TAS of 500 knots divided by 100 equals 5. 5 minus 3 equals 2. 2 what? It is 2 divisions to move the arrow pointing at the compressibility scale to the left. This has the effect of decreasing the initially observed TAS of 500 knots. Now reposition the red cursor through the initial RAS of 280 knots on the inner scale and read off 480 knots corrected TAS on the outer scale. If 10 on the inner scale is lined up with any number between 575 and 675 on the outer scale, an arrow labelled Mach number index appears in the airspeed window. An example best demonstrates its use. If temperature is minus 45 degrees Celsius, Mach number is 0.82, what is TAS and the local speed of sound? Align the Mach number arrow with the correct outside air temperature in the airspeed window. Mach number of 0.82 on the inner scale lines up with a TAS of 482 knots on the outer scale. Opposite the Mach number of 1.0 is the TAS of 588 knots, which is the local speed of sound. Local speed of sound and Mach number calculations may be achieved using an electronic calculator with the following formulae. Local speed of sound is equal to 38.94 multiplied by the square root of temperature in Kelvin, and Mach number equals TAS divided by local speed of sound. For the same example, Local speed of sound equals 38.94 multiplied by the square root of 228 Kelvin, which is the minus 45 degrees Celsius plus 273. This results in a local speed of sound equaling 587.98. The Mach number of 0.82 equals TAS divided by 587.98. Solving for TAS gives 482 knots. The temperature rise scale accounts for kinetic heating of the outside air temperature probe. For example, for an indicated temperature of minus 30 degrees Celsius and a pressure altitude of 25,000 feet, RAS of 200 knots, what is true airspeed? Having calculated a TAS of 297 knots, read across the temperature rise scale to find a temperature rise of plus 9 degrees Celsius. This gives a correct indicated temperature of minus 39 degrees Celsius, which can be used to recalculate a TAS of 292 knots. The minutes to hours and minutes scale is coloured yellow and permits conversion from minutes on the inner scale to hours and minutes on the hours scale. 60 minutes is 1 hour. 120 minutes is 2 hours. Try converting 274 minutes to hours and minutes. There is 270 minutes on the minutes scale corresponding to 4 hours and 30 minutes on the yellow scale. Add the extra 4 minutes equaling 4 hours 34 minutes. Line up the 10 and the 10 and an ISA atmosphere will be created on the CRP-5. At 0 feet, mean sea level, the ISA temperature is plus 15 degrees Celsius, and at 20,000 feet it is minus 25 degrees Celsius. If we now look at the indicated altitude on the inner scale and the true altitude on the outer scale at, say for example, 4,000 feet, we find that in the ISA atmosphere they are the same. At 20,000 feet, there is also no difference between indicated and true altitude in the ISA atmosphere. If we lower the temperature at 20,000 feet, the inner scale moves back, true altitude becoming lower versus indicated. If it were warmer, the inner scale moves forward, true altitude becoming higher versus indicated. Density altitude is the altitude at which the prevailing density would be found. If the temperature is warmer than ISA, density altitude will be higher than pressure altitude. If the temperature is colder than ISA, then density altitude will be lower than pressure altitude. For example, airfield elevation is 5,000 feet, surface temperature is plus 5 degrees Celsius. What is the density altitude? For density altitude, think performance, think airspeed window. Line up the 10 with the 10. At ISA, 0 feet pressure altitude equals 0 feet density altitude. If the elevation of 5,000 feet is lined up with plus 5 degrees Celsius in the airspeed window, 5,000 appears in the density altitude window. The conditions are still ISA. Let's look at a warmer temperature of plus 30 degrees Celsius at the same pressure altitude of 5,000 feet. Line up 5,000 with plus 30 degrees Celsius in the airspeed window. 8,000 appears in the density altitude window. Density altitude may also be calculated using an electronic calculator using the following formula. Density altitude equals pressure altitude plus 120 multiplied by isodeviation.